So recall that we were in the case when lambda was equal to -1. We had this d energy. We bound it with this and this. Just put in a 1 here. Then we make this bound. Okay. And make this as bound, but we didn't say why this was the case. Okay, so let's see this by parts. Okay, so first what we have this. We want to know why this is greater and equal than this. Okay, so we have that minus Laplacian plus m squared u squared norm 2. Okay, so this will be equal to the integral in half-3 of this is 1/4, and so we will have that this is m squared plus xi squared. Now instead of 1/2 we'll have 1/4. Okay. U transform psi squared d psi. Okay, and in the other side we have 1/4 replacing u squared 2, and this we already saw that it is way here xi. So 3 xi. This is u transform psi d psi. Okay, this can be written as squared 1/2. Okay. I'm sorry, this is 1/2. Okay, so and this is, you cancel this and you have xi, so you can see that this is greater than this. Okay, so we have the first one, that is this one, and now let's see the other one. So the other inequality that we want to see is that 1/4 integral R3 or 1 over x convolution u squared x ux squared dx. This is greater than 1 over 4k, and we'll see what is that, this k, from where it came from. Minus Laplacian 1/4 u squared 2 u2 squared. Okay, so let's see from where this comes from. So let's consider the functional ku. Okay, we define this the norm minus Laplacian 1/4 u squared 2 u squared 2 integral R3 well, x minus 2 minus 1 convolution u squared x ux squared dx. Okay, so you can see that we have all this term here down. Okay, k is well defined for all u in h1 I have if u different to 0, and let's try to estimate to bound the denominator. Okay, so we get 1 over x convolution u squared x u x squared, okay, dx. Okay, so we can bound that using what we've used in the first lemma. Okay, so the norm infinity, okay, of the integral, this integral, in our case we have a 1 here, but it's the same, can be bound by the norm infinity of x x to the minus 1 convolution u squared infinity. That's what we already used, and we will use it again. So this integral will be less than equal than the norm infinity of 1 absolute value of x convolution u squared norm infinity and multiply by u square norm 2. Okay, here we used Euler, okay, just like we did before. And now we will use, here we have the norm infinity of this, exactly what we have, and we bound it by this within a constant. We can see that the constant is going to be pi over 2. Okay, so we will use this bound that we use in the first lemma. So this will be less than equal then what we say in lemma 1. The constant is p or pi over 2. Let's write it. Okay, will be the constant pi over 2 norm minus Laplacian 1/4 squared 2 u squared, here u squared norm 2. Okay, so we have this inequality. Okay, and if we want to get this, you can see that we can take this, that is the upper part of the fraction, we can take it down here and then turn this. We will obtain k of u, okay, greater than equal than 2 over pi. This is because we take this here down and then we change, this goes to the upper part and this that is here goes down, obtaining k, but we have to, this constant also turn it upside down and we will obtain, also changing the inequality, that 2 over pi is less than equal than ku. This will be less than infinity, and so we will call k that we have here equal to the infimum ku's, okay, ku's, so that such that u in nature 1/2 or 3, and u is not the function constantly 0. Okay, you can see that k does not diverge because both the denominator and the numerator are bounded by the conservation of energy. Okay, these are parts of this is part of the conservation of energy, and we use this also to bound the solution in h1/2. So now you can see that this is k, let's say, or the infimum is k. If we turn it upside down, we will have this, but we will have this in the denominator, and so to cancel it, we will have to have another term of minus Laplacian 1/4 u squared 2. So that's how we get this bound. We bound this by k as the infimum of this, multiply what we need to cancel this upper part that would be the down part when we have the k in the denominator. Okay, so we obtain this bound. This, if we take common factor this norm, we will have 1/2 minus 1 over 4k norm u squared 2 norm multiplication 1/4 u squared 2. Okay, so we finally obtained the energy u is greater than equal than this. So if we want to obtain a bound just like we did with the defocusing case, we have to have a bound in terms of the norm of my multiplication 1/4. So for that to happen, we will have to ask that u, and in the case u naught squared 2, to be less than 2k, because if this is 2k, then we will have 1/2 and it will be 0, but we will not have a bound that depends on this. Recall that that's what we needed when we did the defocusing case. Here you can see it. We have a bound that depends on the norm 2 of multiplication 1/4. So with this we obtain the bound that we wanted for the defocusing case. A comment to do is that this k satisfies that k will be equal to norm q squared 2 over 2. This will be greater than 2 pi, and this q will be a ground state solution of minus Laplacian q minus 1 over x convolution q squared q equal to minus q. Okay, one can prove that if we, for example, it gives rise to solitary wave solution such as utx equal to for example EIT qx, and with m equal to 0, if you insert this in the equation, we obtain this. Okay, so q in h1/2 will be a minimizer for k. Okay, that would mean that k of q will give k the infinite. Okay, so we finally have that because of this, it's sufficient for global existence to have u naught squared 2 less than q squared 2. Okay, and that will be sufficient for global existence for lambda equals 2 minus 1. Okay, but by rescaling we will have the case lambda negative. Okay, so this is the condition that comes from here. Okay, because if k is equal to norm q squared 2 over 2, we insert it here, we will obtain this, the condition. Okay, so this is the proof for global existence in h1/2 of the Schrodinger relativistic equation, or Boson Stars equation.